Alright, we are going to talk about the nature of energy. So what is energy? We are going to go ahead and watch a quick video.
What do we mean when we talk about the energy in a candy bar? Or conserving energy? Or finding alternative energy sources? What exactly is energy? Energy is a property used to describe a wide variety of things, from the tiniest particles to the most complex systems. But unlike physical properties, such as color, length, or temperature, it's better understood by what it can do than how it looks or feels. The standard definition of energy is the ability to do work. In other words, it's the ability to create some sort of change in an object, whether it's the object's location or the motion of its atoms. All objects store energy, but they differ in the amount and forms of energy they carry. For example, chemical energy is stored in the bonds that hold molecules together. Potential energy can be stored in an object's position, like this apple hanging from a tree. And when the apple falls to the ground, that potential is transformed into kinetic energy, or the energy of motion. Not only does energy come in many forms, but we can also convert it from one form to another. For example, we make use of the chemical energy stored in fuels like oil and coal by burning them. When we do so, we convert their chemical energy into thermal energy, or heat, to warm our homes. Or we can use fuels to produce electricity, the energy carried by electrons moving through a wire. So if we can convert energy from one form to another, why are people so concerned about conserving it? The fact is, not all energy forms are equally useful, and not all conversions are easy to do or equally efficient. Take electrical energy, for example. We use it to power all kinds of technological devices. However, as the electricity drives computer processors and lights up TV screens, it's transformed into other, less useful forms of energy, especially heat and light. That energy isn't lost. It still exists, but once released into the surrounding environment, this relatively small amount of heat and light can't be recaptured and converted back into electrical energy. And so, whether it's fossil fuels today or large-scale alternatives in the future, we'll continue to need new energy sources if we want to keep our high-tech, electrified world running.
So, after watching this, you should try to answer these questions. So I'm going to ask you to pause the video and answer these two questions in your interactive notebook. The first one is, what are a few of the different forms of energy that you heard discussed in the video? And provide one example of an energy conversion. So when one energy becomes two different ones. And if you need to rewind and rewatch that video again, it may not be the worst idea. But you should be able to answer those two questions in your interactive notebook. So go ahead and pause right now. Alright, so you should have those questions answered in your notebook. We're going to go ahead and move on now. So energy is the ability to do work. In other words, to change the position of something. There are different forms of energy. The six main ones are mechanical, chemical, thermal, radiant, nuclear, and electrical. How we measure energy is in a unit called joules, and it's represented by a capital J. So when I ask you to calculate energy, you'll be calculating it in joules. Energy transformations. Now, we talked a little bit about this when we talked about the law of the conservation of mass. So remember we said mass cannot be created or destroyed, it can only change form. Well, energy is the exact same way. The law of the conservation of energy says that energy can never be created or destroyed, just converted from one form to another. So for example, okay, we have a light bulb, which turns on with electrical energy, okay, but then is transformed into light energy and thermal energy. If you've ever touched a light bulb, okay, it's hot, okay, so it changes into light energy and thermal energy. Kinetic energy. So this is another form of energy that can be a little bit abstract or kind of hard to understand, but kinetic energy is the energy in the form of motion, so movement. It depends on the mass. Remember, that's how much matter is in something. And the velocity. Remember, velocity is speed with the direction that something is moving. So, in other words, up here, this little kid who is sitting at the top of the slide is not moving, and so it does not have kinetic energy. But this child who is moving down the slide has kinetic energy. And the amount of kinetic energy depends on the mass of the child and how fast and in what direction the child is moving. So going down a slide, okay, that is the direction, and how fast they're going down the slide we'd be able to calculate the kinetic energy of that child. So potential energy is energy that is stored in the object. So like we said, the child who's not moving, who does not have kinetic energy, at the top of the slide, that would be a example of potential energy. So when she does go down the slide, she will gain kinetic energy, but until then, not moving at the top, she has a potential energy. So there are different types of potential energy. There's elastic potential energy. This is energy stored by something that can, I don't know why that's there. This is energy stored by something that can stretch or compress. Okay, it's elastic like a rubber band. Okay, it can either stretch or it can compress, get smaller. An example is a rubber band or spring. So when a spring is just sitting there, it has elastic potential energy. But when you compress it, it's going to get more potential energy, more elastic potential energy, because when you let it go, it's going to have a large amount of kinetic energy. There's chemical potential energy. This is energy stored in chemical bonds. We talked a little bit about this when we talked about chemistry, in that we talked about the different types of bonds. Different bonds have different amounts of energy, and the energy is what is stored in those bonds. So when I have H2O, remember that's two hydrogen molecules, and they each have a bond with oxygen. Okay, that is those chemical bonds have energy that is holding that molecule together. Now, when you heat it up, you break those bonds, and that energy is released, allowing those molecules to move faster and faster. Remember that that's temperature. So, an example is a glass of milk has a chemical potential energy, CPE, chemical potential energy, until you drink it. Then calories are used as energy for your body. So it has a chemical potential energy, and then we're going to use that energy as the milk gets broken down for energy by our stomachs. Then there's gravitational potential energy. This is anything that can fall, has gravitational potential energy. Remember, this depends on the mass and, and acceleration. Remember that? Force equals mass times acceleration. Acceleration due to gravity. So the force is calculated through that. So gravitational potential energy is anything that can fall and anything that can fall has gravitational potential energy. Okay, and remember, the gravity due or acceleration due to gravity is what we used when we were calculating our weight on other planets. And so gravitational potential energy would change depending on our mass on that planet and the acceleration due to gravity. So a rock that is on a ledge, it has the potential to fall, so it has a gravitational potential energy. If you have an apple hanging from a tree, as they showed in the video earlier, that has a gravitational potential energy because it has the potential to fall. All right, so that is all we are going to do for today. Write down any questions that you have. Thank you.